Okay, we're going to get into some of the gas law math problems now. This first one is a Boyles Law problem, which is a pressure-volume relationship. As you recall, this is the formula for Boyles Law. P1V1 equals P2V2. So it's a pressure-volume relationship. As you read, it says the initial pressure is 3.54 atmospheres. And it says the initial volume is 23.1 liters. And it wants to know what the new volume will be if the pressure is decreased to 1.87 atmospheres. So there's your final pressure, final volume, we do not know. And so this is just an algebra equation. Basically, if I divide both sides by 1.87 atmospheres, 1.87 atmospheres will cancel. If I divide over here by 1.87 atmospheres, the atmospheres will cancel. I multiply and divide, and I end up with 43.7 liters. Look at your answer. Does it make sense? Pressure decreased, volume goes up. Yep, makes logical sense. Number of sig figs has been conserved. Here's another Boyles Law problem. Okay, it looks like we know we have a pressure of 34.6 atmospheres. I do not know the volume that relates to that. Let's see. We do have a pressure of 2.94 atmospheres, and the volume at that pressure is 456 liters. Okay, so I want to solve for x, so if I divide both sides by 34.6 atmospheres, it'll cancel over here. 34.6 atmospheres. Atmospheres cancel, leaving me with the units of liters, which is awesome. I multiply and then divide. My answer, 38.7 liters. Number 16 is another Boyles Law problem. Okay, it looks like we have an initial pressure of 7.43 atmospheres, and it occupies a volume of 45.1 liters. I do not know the final pressure, but I do know that the final volume is 18.4 liters. Once again, you got to get x by itself. So if I divide both sides by 18.4 liters, it goes away. 18.4 liters. Liters cancel. Multiply and divide. And my answer should be 18.2, the unit atmospheres. Okay, this time we have a Charles Law problem because it is relating volume and temperature. The main thing you have to recall, so here's the formula, initial volume divided by initial temp is the final volume divided by the final temp. You have to recall that the temperature must be in the units of Kelvin. So you have to convert that first off. And so let's see, I have an initial volume of 2.45 liters, and then the temp is 0 degrees Celsius. Well, I remember if I want to convert, I take the temperature in Celsius plus 273, and that is going to give me my Kelvin temperature. Well, if Celsius is 0, 0 plus 273 is 273 Kelvin. Okay, I do not know the final volume, but I do know the final temp is 52 Celsius. So if I take 52 plus 273, it should be 325 Kelvin. Okay, I want to solve for x. I need to get it by itself. So I want to cross multiply. So I want to put the 325 Kelvin over here. The Kelvin will cancel, leaving me with liters. So I multiply, then divide. The answer, 2.92 liters. This is another Charles Law problem. This time I do not know the volume, but I do know, let's see, 285 Kelvin. That's the 12 degrees Celsius. And then I know, let's see, The other volume is going to be 75 liters. And then negative 28 Celsius, so 273 minus 28 is 245 Kelvin. So if I want to solve for x, I'd cross multiply. So the 285 Kelvin comes up here. Kelvin cancels. Multiply. And then divide. And it should be 87.2, the unit left, liters. Okay, in looking at this problem, you notice that it does mention a pressure, volume, and temp for a gas, and so you may be led to believe, oh, I should use the combined gas law. But the thing you will notice is that the pressure remains the same. It is 1 atmosphere in the beginning and the end. So you can just omit it. You could use the combined gas law, the P1 V1 over T1 equals P2 V2 over T2. You'll get the exact same answer, but I mean, why even bother if you don't need it? If the pressure doesn't change, I would just omit it. So let's see, let's start out with a volume of 5.65 liters, and then the temp is 300 Kelvin. It's 27 plus 273. And then let's see, the final volume is 6.69 liters. And then let's see, the final temp is what we're trying to solve for. All right, so we need to solve for x. I want to get x by itself, and not only do I want to get it by itself, but I want to get it in the numerator of a fraction. I do not want it in the denominator. So basically what I'm going to do, I'm going to have to do some cross multiplication and division. If I rearrange this problem, I'm going to get x equals 6.69 liters times 300 Kelvin divided by 5.65 liters. If you've set this up correctly, the liters should cancel because you have them in the numerator and the denominator. You're left with Kelvin, which is awesome because we're looking for a temperature. So if I multiply and then divide, my answer should be 355 Kelvin. And if the problem doesn't ask you to put it back into Celsius, I wouldn't. I would just leave it in Kelvin. It's just one more opportunity for you to make a careless error. So if it doesn't ask for Celsius, leave it in Kelvin. Okay, with this problem, I must use the combined gas law. Why? Because we have pressure, volume, and temperature, all three variables, and they're all changing, so therefore I must use the combined gas law. So pressure, volume divided by temperature equals pressure, volume times temperature. Okay, so let's start filling in what we know. So it looks like I have an initial pressure 0.747 atmospheres. I have an initial volume of 11 liters. I have an initial temp of 286 Kelvin. All right, and let's see, final pressure 1.18 atmospheres. I do not know the final volume. That's what I'm trying to solve for. And let's see, the final temp is 329 Kelvin. And so I need to get x by itself, so I'm going to cross multiply and divide. So I'm going to get 329 Kelvin up here and 1.18 atmospheres down in the denominator. These go away. You'll notice Kelvin goes away. Atmospheres cancel. I'm left with the unit of liters, which is good because I'm trying to solve for liters. And so I'm going to multiply and divide my answer, 8.01 liters. This is another combined gas law problem. So I'm going to start 4.55 atmospheres. Initial volume is 3.65 liters. Initial temp is 336 Kelvin. Okay, let's see, the final pressure, 2.75 atm. I do not know the volume. I do know the final temp is 238 Kelvin. So I'm going to cross multiply and divide. So 238 Kelvin comes up here. And the 2.75 atmospheres comes down here. Atmospheres cancel. Kelvin cancels. I'm left with liters. If I cross multiply and divide, I get 4.28 liters. Okay, we're going to finish out with a few ideal gas law problems. I know these are ideal gas law problems because they mention the number of moles. So pressure volume equals number of moles gas constant temperature. Okay, let's see. I have initial pressure of 1.5 atmospheres. I have an initial volume of 8.56 liters. The number of moles I do not know. That's what I'm trying to solve for. Because my pressure is in atmospheres, I'm going to use 0.082 atmosphere liter per mole Kelvin. And then the temp is 273 Kelvin. How do I solve for x? You got to divide both sides by 0.082 atmosphere liter per mole Kelvin. And then 273 Kelvin. These cancel. Atmospheres cancel. Liters cancel. Kelvin cancels. The only unit you're left with is moles. And so I multiply and divide. You get 0.57 moles. Here's another ideal gas law problem. I have 1 atmosphere. The initial volume is 2.70 times 10 to the 6th liters. The number of moles I know, 1.0 times 10 to the 5th moles. That gas constant I know, 0.082 atmosphere liter per mole Kelvin. And then that unknown. Okay, we have another ideal gas law. I do not know the pressure. The volume is 5.50 liters. I have 2.5 moles. That gas constant, because it's in atmospheres, is 0.082 atmosphere liter per mole Kelvin. And then the temp is 300 Kelvin. Okay, if I divide this by 5.50 liters, okay, you'll notice that the liters cancel, the Kelvin cancels, the moles cancel. You're left with atmospheres, 11.2 atmospheres when you multiply and divide. Okay, one last ideal gas law problem, 1.25 atmospheres. We do not know the volume. The number of moles is 5 moles. Because it's in atmospheres, again, R is 0.082 atmosphere liter per mole Kelvin. And then the temp is 295 K. If I divide both sides by 1.25 atmospheres, they go away. Atmospheres cancel, moles cancel, Kelvin cancels. I'm left with liters. The answer, 96.8 liters.